It begins with a faint shimmer in the dark, a single thread of reflected sunlight drifting through the abyss that separates the planets. No one sees it with the naked eye. No one feels its arrival. The solar system. A realm that has existed for more than 4.5 billion years, continues its unhurried rotation around the sun, unaware that a visitor from an impossibly distant origin is already touching the edge of its domain. Far beyond Neptune, where the concept of daylight becomes only a suggestion, something small, cold, and ancient is coasting inward. Its path is steep and careless, the sort of trajectory that nothing born from the sun would ever follow. It is an intruder on a scale that the Earth has only rarely witnessed. The astronomers who later trace its orbit will speak of it with a quiet sense of awe. It is not a typical comet, not a dusty relic shaped by our planets, and not a survivor from the Oort cloud. It carries a chemical heritage written in molecules formed around another star. It belongs to no known family, no recognized gravitational lineage. It is simply drifting, moving through the galaxy, on a journey that began long before humans learned to make fire. It is ancient in a way that mocks human years, carrying frozen memories of a distant stellar nursery that collapsed and brightened ages before human history existed. Yet this is only the first part of the mystery, because as the newcomer glides inward, instruments begin to whisper of something else. Not a single nucleus, not a lone traveller, but faint echoing signals. They appear as scattered dots, almost too weak to notice. They linger in frames taken hours apart. They shift slightly, never enough to draw attention on their own, but just enough to create unsettled questions among those who stare at the data for too long. Even before anyone dares to suggest the possibility, the signs gather like soft footsteps behind a solitary wanderer. There is a sense that the comet is not entirely alone. In raw telescope images, the visitor is little more than a smudge. Its coma is small and pale, its tail short and hesitant. But the surrounding darkness seems to hide something more. The same pixels that are meant to reveal open space occasionally conceal tiny sparks aligned almost perfectly with the comet's motion. They're easy to dismiss as noise, cosmic rays, calibration errors, or reflections of distant stars. Easy, that is, until the same glimmers appear, again in different exposures, in different datasets captured by different telescopes. Their persistence becomes uncomfortable. As the weeks pass, astronomers begin to speak of the visitor in more poetic terms. They imagine a lone wanderer stepping across a threshold while dragging a faint procession behind it. Some compare it to a seed released from a fractured world. Others envision a broken necklace of ice and dust, its pieces scattered by ancient forces, yet still drifting as an extended family. The very thought is unsettling. If this object is truly accompanied by a swarm, it means the solar system is being pierced not by one interstellar body, but by many. It suggests that what the telescopes are seeing is only a small illuminated corner of a much larger structure sliding past the sun. The name that will eventually enter scientific literature is 3I Atlas, the third interstellar object ever confirmed. The third visitor, whose path carries no signature of the sun's gravity, no sign that it originated here. The first was unusual enough. The second was fragile but understandable. This one arrives with a suggestion of something deeper. A coded message written in the geometry of space and the mathematics of orbital motion. A comet from another star system should be alone. It should be a wanderer thrown out by the violence of its origin. The presence of companions would be improbable, their coherence even more unlikely, and yet hints begin to align. Many nights later, after careful analysis, someone finally asks the question out loud. Could these faint traces be fragments? Could the visitor be the central remnant of a long disrupted body, with its pieces stretched out across an invisible corridor in space? Or could it be part of a stream, a filament of interstellar debris drifting through the galaxy, of which 3I Atlas is merely the brightest or closest representative? These questions appear quietly At first tucked into emails, exchanged after midnight, mentioned in teleconferences where no one wants to sound too speculative. Still, the atmosphere shifts. The idea refuses to stay small. A comet from another solar system is already a scientific gift. A comet accompanied by a swarm would be something far stranger. It would be a sign of processes that humans have never directly witnessed. Stellar collisions, violent planetary migrations, tidal shredding under binary stars, or ancient icy belts torn open by passing giants. To imagine a swarm following a single nucleus is to imagine cosmic events that unfold over millions of years. It invites a sense of scale that overwhelms human perspective. A swarm implies lineage, history, destruction, and survival. As the visitor drifts closer to the warmth of the inner system, its presence becomes more tangible. The scientific community watches carefully, aware that such an object may not return for another million years. The comet leaves behind a faint ribbon of ionized particles carried by the solar wind, like a painter brushing a thin line across the void. But the pieces behind it leave almost nothing. No tails, no bright signatures, only gravitational hints so subtle that they must be extracted from stars that shift by fractions of a pixel. They are nearly invisible, yet they appear to be real. This delicate imbalance between certainty and doubt creates a tension that permeates every discussion. The visitor is here, the traces are here, and no one yet understands how they belong together. The solar system has been a stage for billions of years, yet every so often the universe sends an actor no one has met before, speaking a language that must be decoded through light motion and mathematics. 3i Atlas is one of those actors, and the faint swarm behind it is the pause between its footsteps, the quiet accompaniment that transforms a solitary passage into something larger and more enigmatic. For now, the astronomers wait, watching as the stranger glides deeper into their world, its silent entourage drifting in its wake like whispers carried through interstellar night. It began as many astronomical revelations do not with triumph, but with routine. On a quiet night in the Chilean desert, the Atlas survey followed its usual rhythm. The system was designed for vigilance, scanning the sky for anything that might threaten Earth. Its purpose was planetary defense. Its duty was to notice change. Every clear night, the telescope swept across thousands of square degrees, gathering faint light from stars, galaxies, and the endless interstellar dark. Most of what it captured was familiar. Most of what
Tại
it
sao map
flagged were
Chile,
harmless
hệ thống
near-Earth
Atlas quét bầu
objects,
trời như mọi
orbiting
đêm,
debris
chỉ nhằm
or
tìm vật thể nguy
passing
hiểm cho trái đất.
asteroids.
Tại sa
But on
mạc
this
Chile,
particular night,
hệ thống Atlas
something
quét
different
bầu
drifted
trời
through
như
the
mọi đêm,
field.
chỉ
The
nhằm
raw
tìm vật thể
images
nguy hiểm cho
showed
trái đất.
nothing remarkable at first. A slight
3i
streak, a
Atlas
dim
is the
spot, a
third
faint
interstellar
movement
visitor ever
across a grid of
detected,
stars.
but perhaps the first
The
not
software
traveling
that
alone.
combed through these images flagged the object only because it moved in a way that suggested it was not part of the celestial background. It was not a star,
Look at the
not a
repetition.
galaxy, not a
It's
reflection.
synchronized with the
It
trajectory
moved
spike.
just enough to be interesting,
It can't
but
be
not enough
noise.
to be
We need to
alarming.
alert the director.
A technician noted the detection, logged it, and prepared to move on. The night was long and the sky offered more data than any single person could fully absorb. Hours later, when the data was sent to collaborators across the world, the object still did not stand out. It was one among thousands of faint detections produced every night. But the orbital processing pipeline caught a small irregularity. The numbers did not converge as expected. The motion was neither consistent with a nearby asteroid nor with a typical long-period comet. It seemed to drift with a speed and angle that suggested something far more unusual. The algorithms tried to force it into familiar categories but struggled. Only when additional observations arrived did the pattern become undeniable. A scientist in Hawaii ran the early coordinates again and again, each time adjusting the parameters, allowing for uncertainties, including new measurement points. With every pass, the trajectory grew stranger. It pointed not from the direction of any known cometary reservoir, but from deep interstellar space. The error margins shrank. The predictions aligned. There was nothing the sun could have done to place the object on such a path. Its approach speed was too high, and its inclination too sharp. It was coming in with the kind of freedom only an object born around a distant star could possess. The realization did not happen all at once. It formed quietly in the minds of those who studied the numbers. The astronomers involved knew well the history of false alarms. A slight mismeasurement could bend a trajectory in misleading ways. A bad calibration could produce illusions of exotic origins. And yet the data kept accumulating, and each new piece strengthened the conclusion. The object was not gravitationally bound to the sun. It had never been. It was simply passing through the solar system the way a ship might pass near a distant harbour without stopping. Additional observatories were alerted. Time on telescopes is precious, fiercely competitive, and governed by scientific committees. Requests normally require justification, planning, and scheduling. But interstellar visitors do not wait. They do not respect human calendars. They glide on trajectories shaped by forces older than the Earth. And so as news of the strange newcomer spread, astronomers set aside ongoing projects to secure observations. The sky had presented an opportunity that could not be ignored. Within 24 hours, telescopes across the United States, Chile, Europe, and Australia had confirmed the object's reality. It moved as predicted. It brightened slightly as sunlight struck its fragile surface. Its coma remained faint but discernible, a thin, delicate haze barely escaping the nucleus. Observers estimated its size, its reflectivity, and its rough rotation. The numbers came back consistent with a cometary body, but one unlike any they had catalogued before. It was too faint to be ordinary, too slow brightening to match typical activity levels, too chemically muted to resemble comets, known to originate near our sun. Then in a late-night meeting held across multiple time zones, someone made the comparison that changed the mood. The orbital elements resembled those of the first interstellar visitor humanity had ever observed. The memory of that earlier discovery still lingered among astronomers, not only for its uniqueness but for its mysteries, which had sparked debates that continued to this day. If the new object followed a similar arc, then this was not merely another comet. It was part of a category that had only recently been recognized. The scientists named the object 3I Atlas, marking it as the third interstellar object officially discovered. The first had been an elongated, tumbling fragment that challenged the imagination. The second had been a ghostly, fragile comet with a tail as delicate as breath. Now came the third, and with it an entirely new flavour of strangeness. It was neither a sharp fragment nor a crumbling snowball. It was something subtler, something colder, something more reserved. A quiet visitor, carrying an ancient silence. As more data arrived, astronomers pieced together the conditions of its discovery. The night was unusually still. The seeing conditions were stable. The faint object was captured at precisely the right moment, during the brief period when it was bright enough to be noticed, but before it faded back into obscurity. Had the weather shifted? Had the software filtered the detection differently? Had the telescope aimed a few degrees away? The visitor might have slipped through unnoticed, continuing silently around the sun and then back out into the void. The uniqueness of discovering an interstellar comet lies not in the object itself, but in the improbability of seeing it at all. Space is vast beyond comprehension, and the distances between stars render such detections almost miraculous. The idea that a tiny icy body, only hundreds of meters across, could be spotted drifting through a sky containing billions of stars speaks to the precision of modern instruments. The fact that it was seen at all is a testament to human curiosity and technological progress. Yet even at this early stage, something about the object resisted easy interpretation. It lacked the dramatic flair that many comets exhibit as they approach the sun. Its tail was more suggestion than statement. Its brightness remained modest. The chemistry inferred from early spectra suggested an unusually low abundance of certain volatiles, a strange profile for a comet, unless it had spent millions of years in interstellar radiation fields, slowly losing more delicate materials. The object seemed old even by cosmic standards, shaped by a journey through regions of space where starlight rarely reaches. But the most intriguing feature of the early discovery was not the comet itself, it was what surrounded it. In some of the deeper exposures, small faint specks appeared near the object's path. They were inconsistent. They flickered in and out of frames. They did not match any known sources. They moved just slightly relative to the main object. Astronomers dismissed them, at first assuming they were noise or artifacts. The skies full of cosmic rays, scattered reflections, and digital irregularities. Any one of these could have explained the anomalies. Still, something about those small specks unsettled the researchers who noticed them. They appeared too often. They clustered too consistently near the object. And though no one said it aloud during the first days, the idea grew silently in the background. What if 3i Atlas was not alone? What if the strands of data hinted at a larger structure, a group or cluster following the same path? A comet with companions would be unprecedented. An interstellar comet with companions would be astonishing. For now, the speculation remained quiet, contained within private messages and late-night discussions. The scientists focused on confirming the object's trajectory, measuring its motion, and understanding its composition. But the faint points lingered. They stayed embedded in the data like subtle fingerprints, waiting to be interpreted. And as the days advanced, the first hint of a swarm, following 3i Atlas, began to take shape, a whisper, hidden beneath the signal of a single wandering flame in the darkness. The confirmation did not arrive through a moment of revelation, but through a long chain of mathematical refinement, each step shaving away uncertainty with the cold precision of orbital mechanics. Every new observation added a fragment of truth, and those fragments began to arrange themselves into a pattern that could not be ignored. At first, astronomers approached the numbers with caution. A faint object detected over only a handful of nights is notoriously difficult to classify. Its path can resemble many things. A poorly constrained long-period comet can mimic an interstellar trajectory. An asteroid with limited data can appear to follow a hyperbolic arc. Only time and additional measurements can force the orbit to reveal its true nature. The earliest calculations wavered between several possibilities. Some solutions placed the visitor on a distant, slow curve, with a period so long it effectively behaved like an unbound object. Others hinted at a more dramatic path, one that would never circle back toward the outer reaches of the sun's influence. The distinction between these scenarios lies in a single number: the eccentricity. A value of 1 indicates a parabola. A value above 1 signals a hyperbola, and a hyperbola means escape. An orbit above that threshold means the object is not simply wandering temporarily. It means the object was never part of the solar system to begin with. To confirm eccentricity requires precision. The telescopes measured the object's coordinates against background stars each night, reducing the error bars. The differences were minute shifts measured in fractions of arc-seconds, but the universe is governed by such tiny details, and slowly as the dataset expanded, the eccentricity pushed upward with firm insistence. The trajectory could not be forced into any bound solution. With each recalculation, its fate became clearer. This visitor would not remain. It had arrived from outside and would depart the same way, carrying its ancient cargo of ice back into the dark between the stars. The confirmation triggered a mixture of excitement and restraint. Interstellar objects are rare beyond comprehension. The first detection had shocked the world. The second reinforced the idea that such encounters might not be as uncommon as once assumed. The third would solidify the notion that the galaxy is filled with errant fragments, each ejected by violent processes in distant systems. Yet even among these remarkable events, this new visitor felt different. It was quiet, modest. Its lack of showiness made the interstellar label even more curious. The process of confirming its origin spread across multiple institutions. Observatories in Europe provided higher resolution tracking that tightened the projections. An Australian facility contributed southern hemisphere data that filled gaps in the trajectory. A radio telescope in Canada added timing measurements that further refined the speed. In Hawaii, researchers revisited each frame to ensure no errors tainted the early inputs. They cross-referenced star positions corrected for atmospheric distortions and examined the device's calibration logs. Once all these pieces were assembled, the path of 3I Atlas became unmistakable. It approached the solar system with a velocity far exceeding anything a bound object could possess. Its inbound speed suggested an origin so distant that its momentum had not been significantly altered by the sun's gravity. It was falling inward, yes, but not enough to capture it. The sun exerted a pull, but the visitor's momentum was ancient and immense. It would merely dip through our planetary system before returning to the wider sea of the galaxy. This moment carried a quiet emotional weight. Every interstellar object that enters the solar system is a message from another world. Not in any communicative sense, but in the sense of origin. To confirm that 3I Atlas was interstellar meant acknowledging that somewhere perhaps tens of light years away, a star once hosted this icy traveller. Perhaps it was part of a planet-forming disk. Perhaps it grew within a ring of frozen debris. Perhaps it was shaped by the gravitational tides of a young exoplanet. Whatever story it carried, its journey began beyond the reach of the sun, in regions that humans have never directly seen. But there was another layer to the confirmation that puzzled researchers. The trajectory was hyperbolic, but not wildly so. Its excess velocity was modest lower than some theoretical models predicted for typical interstellar ejecta. This was peculiar. Many interstellar fragments are expected to be accelerated violently during their ejection, often gaining speeds far higher than the one measured for 3I Atlas. A low excess velocity could indicate a very old ejection event. Perhaps millions of years had passed, allowing gravitational drifts to dilute the initial blast of momentum. Or perhaps the object had originated not far from the sun, in galactic terms only a few tens of light years away. More intriguing still was a subtle detail buried within the early trajectory plots. The path showed a faint clustering in angular momentum that did not match the randomness expected of a single, isolated object drifting through the galaxy. Some astronomers noticed it and made quiet notes. The orbital plane seemed tilted in a way that resembled certain models of interstellar streams. Groups of fragments can form extended structures when they are ejected together or when tidal forces stretch them over vast distances. To detect such alignment would be extraordinary, but the data was not yet sufficient to draw conclusions. Meanwhile, the comet's movement was compared to simulations of bound long-period comets to exclude the possibility that it originated from the Oort cloud. The results were decisive. No known gravitational scenario could place it on its observed trajectory. The only explanation was that the object carried an independent history, one tied to its birth system, not to the sun. The Oort cloud, while vast, could not account for this path, nor could interactions with giant planets. The object arrived from an entirely different gravitational environment. The researchers updated their reports. The designation became official. The object was interstellar confirmed beyond reasonable doubt, but this clarity only deepened the mystery of the faint specks seen near its path. If the main body followed a hyperbolic arc from deep space, then anything following the same arc likely shared its origin. Each companion, if real, would be a fragment from the same ancestral system. The implications were profound. Such a swarm could reveal details about how planetary systems form and dissolve. It could provide evidence of catastrophic events in other star systems, events too distant for even the most sensitive telescopes to resolve directly. The confirmation of the trajectory was a triumph of observation and mathematics. It transformed a dim smudge in the sky into a cosmic traveller with a measurable past and a predictable future. Yet it also raised unsettling questions. Why did the object arrive with such subtlety? Why were there faint companions that should not exist? Why did its velocity fall within such a narrow range? Why did the orbital plane hint at something more structured than randomness? These questions lingered in the minds of astronomers as they continued to monitor the visitor. The path was now certain. The origin was now known. But the meaning of the faint traces behind it remained obscured by distance and darkness. And as 3I Atlas drifted closer to the Sun, the mystery only began to unfold, pulling researchers deeper into a puzzle that stretched across interstellar space. As the confirmation of 3I Atlas's interstellar origin solidified, the scientific community shifted from cautious curiosity to focused investigation. A visitor from another star system is not simply a point of interest. It is a rare opportunity, the kind that may not return within a human lifetime. Once the trajectory became undeniable, the next step was to gather every possible photon of light it produced. And so across continents and time zones, observatories began to turn their instruments toward the faint traveller moving silently through the outer solar system. The earliest detailed images came from large ground-based telescopes whose mirrors carved the desert air with precision. In Chile, the VLT captured long exposures that revealed the nucleus as a tiny condensed core surrounded by a delicate breath of gas. The coma was thin and controlled, lacking the vigorous jets seen in many comets native to our system. This restraint suggested an object shaped by a different cosmic environment. The surface seemed old and hardened, its volatile deposits likely depleted by millions of years of exposure to galactic radiation. At the same time, instruments in Hawaii tracked the visitor from higher altitudes. Their images confirmed the comet's subdued nature. Its dust output remained mild, and its tail appeared narrow, almost hesitant. It was as though the comet carried an exhaustion acquired from a journey through regions where sunlight rarely touched its surface. The absence of dramatic outgassing allowed a clearer view of the nucleus than typically possible, with active comets giving astronomers a chance to study its solid form more directly. But the most revealing portraits came from space itself. Observatories far above the Earth's atmosphere can capture wavelengths unreachable from the ground. The first request for observations went to the Hubble Space Telescope. After careful scheduling, Hubble directed its gaze toward the faint visitor. The resulting images were sharp, serene, and deeply detailed. The nucleus appeared as a crisp point of light encased in a subtle halo. The surrounding dust cloud showed a uniformity uncommon among younger comets. Some scientists proposed that this evenness might indicate a surface covered by grains, size sorted by millions of years of interstellar drift. Shortly afterward, the James Webb Space Telescope gathered infrared data offering a portrait not of shape, but of chemistry. Its instruments traced the faint thermal signature of the nucleus and identified weak signals from volatile ices. The chemical blend appeared distinct from those found in typical solar system comets. Certain compounds present in most long-period comets were muted or missing. Other signatures rarely observed were surprisingly pronounced. This difference did not surprise researchers. Interstellar comets are expected to carry fingerprints of their birth environments, and those environments vary across the galaxy. What intrigued scientists was the subtle balance of these compounds, which hinted at an origin region colder than many known protoplanetary disks. The contrast between Hubble's crisp optical images and Webb's glowing infrared structure painted a richer picture than either could alone. Together they suggested a nucleus that was compact, dense, and coated with ancient residues. Webb's data even hinted at thermal patterns suggesting uneven heating across the surface, possibly due to buried patches of volatile material awakening as sunlight reached them. These thermal patches could explain why the coma, though faint, remained stable and persistent. Other observatories joined the campaign. Radio telescopes detected faint emissions from hydroxyl radicals, confirming the presence of water ice sublimating slowly into space. Sub-millimeter instruments mapped out grains of dust drifting away from the nucleus, revealing a size distribution skewed toward larger particles. This pattern hinted at a surface crust that resisted fragmentation a trait typical of bodies that have endured long periods of cosmic weathering. All these portraits, varied in method and wavelength, pointed toward a single, consistent truth. 3I Atlas was a wanderer transformed by unthinkable time. It was not young, it was not fresh. Its surface carried scars etched not by planets or moons, but by the emptiness between stars. The low activity, the muted chemistry, the uniform coma, the crust hardened by exposure to galactic radiation, all indicated a body that had drifted through interstellar darkness, long enough to evolve under conditions no solar system object experiences. Yet even as the comet itself became clearer, a deeper uncertainty grew. Against the refined portraits of the nucleus, astronomers noticed faint irregularities in the background. Some exposures contained tiny points that shifted subtly in alignment with the comet's path. They were too faint to analyze chemically, too inconsistent to classify confidently, but their presence lingered. As image after image was aligned and stacked, at least a few of these points continued to reappear. They never matched the positions of stars. They refused to vanish through calibration. They behaved as though they belonged not to the background, but to the visitor's motion. The great telescopes had done their job well. They had revealed the interstellar visitor with remarkable clarity. But by doing so, they had also drawn attention to something far stranger. The more clearly the nucleus appeared, the more difficult it became to ignore the faint companions drifting near it. At first, astronomers dismissed these as noise reflections or remnants of cosmic rays. Yet the persistence of certain points appearing in multiple observations across multiple instruments suggested an unsettling possibility. The visitor might not be solitary. Portraits meant to illuminate a single body had inadvertently exposed the outline of a larger hidden structure. And though no one dared to make definitive claims, the suggestion was impossible to ignore. If these faint specks were real companions, then the visiting comet was merely the brightest ember in a cluster of fragments spread across interstellar space. The next phase of investigation would determine whether these whispers of light were illusions or the first fleeting sign of a swarm following 3I Atlas toward the inner solar system. As observatories continued to gather images from across the electromagnetic spectrum, the scientific portrait of 3I Atlas sharpened. Its nucleus, its coma, its dust distribution, its thermal glow all grew clearer with each passing week. Yet embedded within this progress lay a series of stubborn, quiet irregularities that refused to disappear. They began as trivial footnotes in data logs. They grew into recurring patterns, and eventually they formed a puzzle that demanded attention. Most comets pass through star fields that are rich and noisy. The Milky Way is full of faint background lights, overlapping sources, and transient distortions. Even the best instruments must wrestle with streaks caused by cosmic rays, diffraction from bright stars, and the electronic signatures of detectors. No astronomer unfamiliar with this visitor would have paid much attention to a few scattered dots flickering along the comet's path. But these anomalies persisted in a way that resisted simple explanations. During the earliest nights of observation, the team working with the VLT noted a faint point that appeared slightly ahead of the comet's nucleus. It was barely above the noise floor, insignificant by normal standards. The team marked it only as an artifact. Yet the point reappeared in a subsequent exposure, shifted by an amount that aligned suspiciously well with the predicted motion of the comet itself. At first, this was dismissed as coincidence, but astronomers are trained to distrust coincidences that repeat themselves. Weeks later, researchers at a Japanese observatory detected two similar points flanking the comet's trajectory. They appeared in deep exposures taken hours apart. Again, the easiest explanation was electronic noise. But the motion of these specks was not random. They drifted in a manner that mirrored the comet's movement across the sky. Their brightness fluctuated, yet their positional relationship to the main object followed a pattern too orderly to be dismissed ever again as accidental. Astronomers began to compile these irregularities into a list. Each point was logged with coordinates, brightness, shape, and exposure time. As the list grew, the emerging pattern became more defined. The anomalies tended to cluster along a narrow corridor extending beyond the comet's immediate vicinity, aligned not with the background stars, but with the vector of the interstellar visitor. They were sparse, faint, and inconsistent, but unmistakably present. Some appeared ahead of the comet, some behind it, some slightly to the side, but always within a corridor that suggested co-motion rather than coincidence. To verify this possibility, astronomers performed an exhaustive calibration sweep. They corrected for sensor noise, atmospheric distortion, and tracking errors. They removed cosmic ray hits and reflections. After subtracting these known artifacts, a handful of faint points still remained. They survived every attempt to eliminate them. Their persistence across telescopes and continents forced a new line of questioning. If these points were not artifacts, then what were they? The first hypothesis considered was fragmentation. Comets commonly shed material as they approach the Sun. Jets can break off shards of the nucleus, producing trails of debris that follow behind. Yet fragmentation alone could not account for the distribution of these points. They were too widely spaced, and some were ahead of the nucleus, an arrangement that conventional comet physics struggled to justify. And the timing of the detections did not align with any known outgassing events. The faint objects appeared in regions where the coma was thin and quiet, not turbulent or expanding. Another possibility was dust clumps reflecting sunlight. Comets release dust clouds that sometimes form knots or denser pockets, but these points were too stable, moving too predictably. Dust structures typically disperse rapidly or deform through radiation pressure. The observed specks maintained coherent positions over extended periods, behaving more like solid bodies than temporary dust concentrations. The deeper astronomers probed, the more perplexing the situation became. Some of the faint points showed a shift in parallax that matched the comet's distance. Others exhibited consistent brightness changes as the observer's angle shifted slightly. These details suggested that the anomalies were not distant stars or background galaxies, but objects that belonged to the same spatial neighborhood as 3I Atlas. The idea that they might share its trajectory grew increasingly difficult to ignore. An international collaboration began to cross-reference observations. Researchers in Chile compared their star-subtracted frames with those from South Africa. Scientists in Spain aligned their data with exposures captured in Arizona. Through careful stacking and motion-matching algorithms, they discovered that a small set of these faint objects traced a path nearly identical to the comet's. Not precisely identical, but close enough to hint at a shared origin or a shared journey. This revelation carried an unsettling implication. For one or two fragments to accompany the comet would be unusual, but not extraordinary. But for multiple objects to drift along nearly the same hyperbolic trajectory suggested a structure, a system, a grouping, a relic that had been stretched across space by forces acting over immense distances and timescales. The visitor might not be a solitary wanderer. It might be the brightest member of a dispersed constellation, a travelling stream of icy bodies threading its way between stars. Despite rising excitement, caution remained strong. The signals were faint. The data still carried ambiguities. Without statistically overwhelming evidence, astronomers hesitated to claim the presence of companions. Yet more observations only deepened the pattern. The faint objects continued to appear at the predicted positions. Their slow drift across the star fields matched the comet's arc. They did not behave like random noise in any traditional sense. There was a moment late in the analysis when the discussion shifted from possibility to probability. One astronomer summarized it quietly. If these points were artifacts, they would disappear when examined from enough perspectives. Instead, more perspectives made them stronger. This was an inversion of normal experience. Noise loses coherence under scrutiny. Real objects become more coherent. The faint points around 3i Atlas were becoming coherent. It gradually became clear that the anomalies were not merely background clutter, but harbingers of a deeper mystery. They were subtle signals that hinted at a second layer of structure beneath the comet's quiet passage. Something extended, something scattered yet linked, something that followed the comet not like debris trailing an impact, but like members of a diffuse, ancient family moving together across the galaxy. These subtle anomalies, once background irritations, became the first concrete indication that the story of 3i Atlas was far larger than anyone initially believed. And with that realization, the investigation prepared to descend into its next phase, driven by a question that no one yet dared to articulate openly. What kind of cosmic event creates a swarm of fragments and sends them drifting together toward an unsuspecting star? By the time the anomalies could no longer be dismissed, the scientific community found itself confronted with something both exhilarating and deeply disconcerting. A comet arriving from interstellar space is rare enough to command global attention. But a comet accompanied by faint co-moving echoes, drifting quietly through the same corridor of sky, was another matter entirely. The facts accumulated slowly, yet relentlessly, pushing researchers toward a possibility that felt almost mythic. The visitor was not alone. It appeared to be part of something larger, something stretched across millions of kilometers, something too coherent to be accidental, and too faint to reveal itself easily. In early discussions, most scientists avoided giving these irregular points any real name. Scientific caution favors understatement. They were simply anomalies, candidates, possible co-movers, weak signals of interest, but as the evidence mounted, describing them as simple irregularities began to feel inadequate. The objects behaved as though connected not by gravity but by origin. They followed a path similar enough to the comet's trajectory that probability alone could not account for it. If these bodies were truly associated with 3i Atlas, then the phenomenon demanded a vocabulary capable of capturing its scale. The first tentative term to surface in published notes was fragment cluster. This name carried the implication of a breakup event, something that might have occurred when the visitor was still far away, drifting through interstellar darkness. Yet the distribution of the faint companions did not match simple fragmentation. A cluster implies proximity, but these points were dispersed across a broad corridor. Some were ahead of the comet, some behind, and some slightly offset, as though the entire arrangement had been stretched by time and tidal forces across an astronomical gulf. Another phrase quietly emerged in internal communications: associated track. This term described the notion of a population of objects sharing a similar orbital path, but it remained too neutral, failing to capture the extraordinary possibility that the solar system was intersecting with a structure far more ancient and extensive than anything produced locally. The idea of an associated track reduced the phenomenon to a geometrical curiosity. Many astronomers felt it was too modest to describe what the data implied. The conversation shifted again when a European researcher studying starfield subtracted reductions noted that the spacing of the faint co-moving points resembled the elongated distribution of debris streams seen in simulations of disrupted exoplanetary belts. The comparison was subtle but evocative. Instead of a tight cluster, the pattern hinted at a filament, a long, stretched-out arrangement of bodies drifting together through the galaxy. The researcher used the word filament casually and without intent to rename anything, but others noticed its descriptive power. It evoked both structure and fragility, an object moulded not by a moment of violence alone, but by slow interplay with gravitational landscapes spanning parsecs. Still, a filament was not quite sufficient. The word did not capture the fragmented nature of the objects. It did not speak to the ghost-like faintness of their appearance. It lacked the sense of unpredictability and ancient motion that pervaded the observations. What scientists needed was a conceptual framework, a term that could accommodate the existence of multiple faint unbound bodies sharing a trajectory carved not by the sun, but by a distant star system that no longer influenced them. The breakthrough came quietly, in a discussion not of the faint companions themselves, but of their behaviour. An astronomer studying the timing residuals of the comet's movement noted that the faint objects did not appear to form gravitational pairs or groups. They were not orbiting the comet. They were moving independently, yet coherently, as if they had been expelled together from a single parent system and allowed to drift loosely as time stretched their separation. The behaviour resembled numerous simulations of interstellar debris flows predicted by models of planetary system evolution. In these simulations, fragments no longer bound by a central star spread out across unimaginable distances, moving like a cloud of cold embers scattered by a dying fire. No single ember controls the others, yet they drift in similar directions because they once shared the same moment of release. This vision of loosely related fragments wandering together across the galaxy sparked a new interpretation. A researcher in South America quietly described the phenomenon as a swarm. The term was informal, spoken during a conversation rather than written into a paper, but it resonated immediately. A swarm acknowledges independence, yet implies shared origin. It emphasizes multiplicity without requiring gravitational unity. It reflects the faint, scattered, whisper-like presence of the anomalies detected near 3I Atlas. And it aligns with models predicting that interstellar space may be populated not by solitary comets, but by elongated populations of fragments spread across vast distances. Once spoken, the word circulated rapidly. Emails began to refer to the Atlas swarm. Observing proposals mentioned candidate swarm members. Teams analysing deep exposures searched specifically for swarm signatures. The term was not formalised through committee or publication. It emerged organically from the need to articulate a phenomenon that had until then lacked an adequate name. Yet even as the term gained traction, researchers approached it with restraint. Words in science carry influence. To label this phenomenon prematurely could bias interpretations, but the evidence demanded some framework. The faint objects followed the same hyperbolic inclination. They exhibited similar angular drift. Their brightness profiles matched expectations for fragments hundreds of meters across possibly smaller. Their spatial distribution suggested not a recent breakup near the Sun, but an ancient event that had occurred far beyond the heliosphere. The swarm concept fit too well to ignore. It captured both the known facts and the profound uncertainties. It acknowledged the possibility that 3I Atlas was not a solitary wanderer, but a member of a much larger population, all born from a shared origin event. It invited questions about the nature of that event. Was it a catastrophic collision within an exoplanetary system? A tidal disruption near a binary star? A clearing of a distant belt of icy debris by migrating planets? Or something yet unimagined? And as the observations continued, the term swarm began to feel less speculative and more descriptive. Astronomers still avoided definitive conclusions, but they could no longer deny that the faint companions behaved as though part of a shared interstellar structure. In time, the word began to appear in internal reports, then in preprint drafts, always accompanied by caution, but no longer treated as an exaggeration. The invisible swarm had become part of the narrative. It shifted the scientific question from what is 3I Atlas to what kind of cosmic history produces a swarm of fragments drifting together across interstellar space. This shift expanded the scope of the investigation far beyond the comet itself. It cast the visitor not as an isolated object, but as a messenger from a far larger and more mysterious process. What the telescopes had glimpsed was only the beginning. The real challenge was to uncover the nature of the swarm, its extent, its origin, its evolution, and the forces that shaped it. The mere existence of such a structure hinted at a cosmic event so ancient and far-reaching that even the solar system's passage through it would capture only a fleeting glimpse of its scale. And with that realization, the mystery surrounding 3I Atlas deepened, drawing the scientific community toward questions that stretched far beyond any single comet drifting through the light of our sun. When comets were supposed to be solitary, long before 3I Atlas drifted into the solar system, the scientific worldview surrounding comets rested on a foundation so stable that few ever questioned it. For centuries, astronomers regarded these icy wanderers as individual relics, each shaped by its own quiet history, but ultimately solitary in nature. The idea of a comet moving alongside faint companions was almost unthinkable. Comets broke apart, yes, and sometimes shed debris, but for most of astronomy's history, the default assumption was that each nucleus travelled alone, a single remnant following a path conditioned by gravity and sunlight. This belief was not a product of oversight. It was built through centuries of observation. When Edmund Halley first traced the periodic return of his famous comet, he revealed a world where these icy bodies behaved predictably. Their trajectories could be mapped, their returns anticipated, their physical processes modelled. The framework that grew from this work cemented comets as discrete entities whose behaviour could be studied in isolation. Each nucleus was an individual, each orbit a singular arc, each appearance a self-contained event. Even as telescopes improved and astronomers gained access to deeper sky surveys, the essential solitude of comets remained uncontested. Instruments captured tails stretching millions of kilometres, jets erupting from sunlit surfaces, and dust clouds swirling in complex patterns, yet never did these images yield convincing evidence of long-standing companion bodies drifting in tandem. When fragments appeared, they were typically short-lived, born from sudden breakups, faintly luminous for a brief time, before dispersing into diffuse dust clouds. Such events were common, but ephemeral, lacking the persistence or coherence seen in the faint objects suspected around 3I Atlas. The rise of space-based platforms reinforced this perspective. Missions like Giotto Deep Impact and Rosetta captured comets at close range, revealing surfaces marked by cliffs, pits, jets, and ancient fractures. These missions told stories of erosion and alteration, but always of single bodies evolving over long time scales. They offered dramatic evidence of internal layering, seasonal patterns, and volatile reservoirs, yet none suggested that comets sustained structured companionship across astronomical distances. Fragmentation was chaotic, not organized. Debris clouds formed, but they diffused quickly under the competing forces of solar radiation and uneven outgassing. The expectation of solitude carried through to the models of cometary populations. The Kuiper Belt and Oort cloud were understood as vast, diffuse reservoirs filled with objects separated by immense distances. Encounters were rare. Influence between bodies was minimal. Even when comets ventured inward, gravitational nudges from planets altered their paths unpredictably, making the notion of long-term companions statistically improbable. Everything known about their dynamics emphasized individuality rather than cohesion. Yet this traditional picture contained an implicit assumption. It presumed that all comets observed near the Sun shared origins and histories shaped entirely within the solar system. For centuries, that was a reasonable belief. No confirmed interstellar object had ever been observed. The known comets bore chemical ratios, isotopic fingerprints, and orbital behaviors that placed them firmly within the Sun's sphere of influence. The idea that comets from other stars might behave differently remained speculative. Only with the arrival of the first interstellar visitor did this framework begin to shift. That earlier object revealed that some fragments from distant systems could reach us intact, carrying unfamiliar shapes and unusual behaviors. Scientists began to reconsider long-standing assumptions. If a fragment could survive ejection from a foreign star system and cross the void alone, what prevented multiple fragments from doing the same? Could a distant planetary system generate a stream of bodies rather than a single candidate? Could stellar tides or catastrophic collisions shape entire families of fragments? As these questions entered the scientific conversation, the older model of cometary solitude began to feel incomplete. It was not wrong, but it was narrowly defined, shaped only by comets native to the Sun. The possibility that other systems might produce structures entirely unlike our own gained traction, especially as exoplanet research revealed startling diversity in planetary configurations. Some stars hosted hot Jupiters skimming their surfaces. Others held dense belts of debris. Some systems showed signs of violent collisions scattered through their history. These discoveries suggested that the solar system might not be the archetype once imagined. Instead, it might be one of countless possible arrangements. And if other systems differed drastically in their formation, then their debris fields might also differ. They might generate elongated trains of fragments. They might eject groups of bodies simultaneously. They might produce structures shaped by gravitational tides that stretch across interstellar space. Still, these ideas remained theoretical until 3I Atlas arrived, carrying its faint entourage of irregular points. Only then did the disconnect between old expectations and new evidence become impossible to ignore. The anomalies, subtle yet persistent, revealed the first observational hint that the cosmos might occasionally send not just lone wanderers, but clusters. Streams, filaments, swarms shaped by forces operating far beyond the Sun's reach. This moment marked a shift in perspective. What was once considered an absolute that comets are solitary travellers began to look more like a local truth valid only for bodies shaped by the Sun. The arrival of 3I Atlas challenged this assumption by presenting the possibility that interstellar space hosts structures formed under very different conditions. Conditions capable of creating families of fragments drifting together, held not by gravity but by shared origin and shared momentum. And as astronomers grappled with this new possibility, they realized that the story unfolding before them was larger than the comet itself. It required rethinking long-held beliefs. It required accepting that the universe may contain architectures of debris far more intricate than anything the solar system produces. The faint companions trailing through starfields behind 3I Atlas hinted at a heritage written across interstellar miles, a history that pressed against the limits of what comet science once believed possible. With this shift in understanding, researchers turned their attention to the deeper layers of the mystery, prepared to confront the implications of a swarm that refused to fit into any familiar category. Once the possibility of a swarm gained traction, astronomers turned their attention to the mathematics that defined its motion. Orbital mechanics is an unforgiving discipline. It tolerates no ambiguity, accepts no hand-waving, and reveals its truths through numbers that either align or collapse. If the faint companions near 3I Atlas were real, they had to obey the same celestial rules that govern every body moving under the influence of gravity. And yet, as calculations accumulated, the swarm displayed a coherence that strained the neat divisions long embedded in the science of trajectories. The first point of tension appeared in the angular alignment. The candidates detected near the comet traced paths that mimicked its inclination to an extent that felt improbably precise. Coherent inclination among unrelated bodies is unusual. Random fragments from the solar system do not naturally fall into such tidy alignment unless shaped by a common gravitational history. But these bodies were not born within the Sun's influence. Their hyperbolic paths indicated an origin far beyond the Oort cloud, and their unity suggested a framework not easily reconciled with random interstellar motion. Another subtle tension surfaced in their velocity distributions. As researchers compared measurements taken across different observatories, they noticed that several faint objects maintained speeds within an extremely narrow range relative to the main comet. They were neither accelerating away from it nor falling behind in ways expected of fresh debris. Instead, they drifted with nearly parallel momentum. Their spread was so delicate that small differences faded into the background noise. This subtle uniformity challenged the assumption that interstellar fragments should arrive singly and with a wide variety of speeds. Detailed simulations offered insight. If these objects were born from the same catastrophic ejection event in a distant planetary system, their initial velocities could have been similar, allowing them to remain in a faintly elongated structure for millions of years. But preserving such coherence over interstellar distances required a fine balance. Minute perturbations from passing stars, molecular clouds, or galactic tides could easily distort a group of fragments. Yet the candidates near 3I Atlas behaved as though such distortions had been gentle, their distribution stretched but not destroyed. As astronomers modelled these possibilities, another anomaly appeared. The spatial separation between the faint points did not match typical fragmentation signatures. When comets break apart near the Sun, their fragments tend to diverge rapidly. Outgassing forces push smaller pieces away. Radiation pressure alters their paths. Subtle differences in shape or mass change how they interact with sunlight and solar wind. But the objects suspected around 3I Atlas showed separations far too large for a recent breakup, yet far too coherent for random distribution. They sat in a puzzling middle state, neither chaotic nor clustered. This pattern forced theorists to revisit ideas about gravitational memory. If a group of bodies retains a shared trajectory across tens of light years, the memory of their origin must be preserved in their momentum, not in any binding force. In other words, these bodies were no longer connected through gravity. They remained aligned because they had once been part of a system that hurled them outward together. Their orderly motion was a fossil imprint of an ancient event. It was motion as ancestry. The challenge lay in demonstrating that such ancestry could survive the journey. Galactic dynamics is an ocean filled with subtle currents. Stars drag tides of influence behind them. Dark matter alters the background gravitational landscape in slow, almost imperceptible waves. Passing stellar systems perturb the trajectories of wandering debris. Over millions or billions of years, these influences tend to erase coherence among any loosely associated group of objects. And yet the candidates near 3I Atlas hinted that a group could persist if the initial conditions were sufficiently aligned and if the objects were ejected with almost identical momentum. As scientists explored this idea, they found themselves confronting a curious detail. The hyperbolic excess velocity of 3I Atlas was lower than that of other interstellar visitors. Not dramatically lower, but subtly, so falling into a range consistent with fragments ejected from a system undergoing slow orderly disruption rather than violent scattering. Such an event could produce multiple fragments with similar outbound speeds. If these fragments then drifted through space for long periods without encountering strong perturbations, they could stretch into a filament, preserving the ghost of their initial alignment. This interpretation opened the doorway to a far more intriguing question. If 3I Atlas was part of such a filament, was the solar system simply intersecting one tiny portion of a much larger structure? Could countless more fragments be threading through space along the same general vector, too faint to detect but present nonetheless? And if so, how large was this structure? Was it tens of millions of kilometers long or billions? Was it the remnant of a disrupted exoplanetary belt, or was it part of a galactic-scale debris flow shaped by long-term gravitational tides? These questions pushed orbital mechanics beyond its usual domain. The mathematics could describe the motion of each detected body with precision, but interpreting the meaning of their arrangement required integrating observations with theories about planetary formation, stellar evolution, and galactic dynamics. The swarm did not fit neatly into any single discipline. It existed in the spaces between them, an interdisciplinary puzzle that demanded perspectives from many branches of astrophysics. Yet even as researchers debated the implications, the motion of the faint points continued to align quietly with that of 3I Atlas. Night after night, as deep exposures were collected, the coherence persisted. The faint companions showed no signs of drifting erratically. Their presence in star fields remained consistent with expectations derived from the comet's path. In the language of orbital mechanics, their behavior whispered of a shared past, even if their present interactions were virtually non-existent. This quiet stress on the mathematical framework did not break it but expanded it. Astronomers began to realize that interstellar debris might not always arrive as solitary messengers. Some visitors could belong to structures shaped across distances so vast that human intuition struggled to comprehend them. Structures whose existence hinted at violent histories unfolding around distant stars. Structures whose fragments, preserved through time and motion, might occasionally drift through the realm of the sun. The discovery forced a shift in mindset. Orbital mechanics had always assumed that coherence implied gravity, but the swarm near 3I Atlas suggested a different kind of coherence, one born from origin and preserved by the deep calm of interstellar space, a coherence that spoke of stories older than the solar system itself. And as the calculations continued, astronomers realized that they were only beginning to understand the scale of the phenomenon unfolding before them. As the evidence for a swarm accompanying 3I Atlas grew stronger, astronomers found themselves recalling two earlier encounters that had already unsettled long-standing assumptions. These previous visitors had passed through the solar system like brief enigmatic messengers, leaving more questions than answers. Their legacies now resurfaced, casting new light on the strange behavior of the Atlas swarm and offering a backdrop against which this new mystery might be understood. The first messenger had arrived unexpectedly, a small and unusually shaped fragment that swept past the sun with a speed no local object could explain. It tumbled erratically, shifting brightness in ways that resisted easy interpretation. Early attempts to model its shape produced contradictory results. Some reconstructions depicted it as elongated like a spindle, while others suggested a flattened body more akin to a shard. The uncertainty was intensified by its non-gravitational acceleration, a faint yet measurable push that altered its trajectory. Traditional cometry activity could not fully explain this subtle drift, especially given the absence of detectable gas jets. Attempts to reconcile the data produced a spectrum of interpretations ranging from exotic ice sublimation to unconventional structural properties. That first visitor forced astronomers to confront the fact that interstellar objects need not resemble the comets and asteroids that populate the solar system. Its unusual behavior expanded the scientific imagination, introducing the possibility that distant systems may sculpt their debris through processes far different from those familiar to the Sun. The second interstellar visitor, though less visually puzzling, carried its own kind of strangeness. It resembled a classical comet, more closely complete with a distinct tail and chemical signatures that aligned with known cometary profiles. Yet it fragmented in a manner that felt almost excessive, shedding pieces, as though its internal structure had been stretched thin by ages of exposure to harsh cosmic environments. Its disintegration highlighted how fragile interstellar bodies can become after drifting through regions saturated with radiation and micrometeoroid impacts. The object did not simply pass through the solar system. It unraveled before astronomers' eyes, providing a glimpse into the physical consequences of extreme age and interstellar erosion. Both of these earlier visitors revealed patterns that awakened a new sensitivity among researchers. They showed that interstellar bodies could behave in ways that solar system models struggled to predict. They demonstrated that fragmentation could be triggered by faint solar heating after long journeys through cold voids. They illustrated the diversity of shapes, compositions, and internal structures produced by the environments of distant planetary systems. And they proved that the solar system would occasionally serve as a stage for objects bearing histories older than Earth itself. Yet neither of these previous visitors had hinted at the presence of companions. Their mysteries were self-contained, focused on individual anomalies rather than shared trajectories. They challenged scientific expectations, but remained singular events. The faint points following 3i Atlas introduced a new dimension, entirely multiplicity. Instead of a lone fragment, astronomers were now confronted with an arrangement that suggested continuity, structure, and possibly even heritage across astronomical distances. What made the comparison intriguing was not similarity, but contrast. The first visitor displayed peculiar motion, but no swarm. The second showed vulnerability to heat, but no alignment with additional bodies. 3i Atlas, by contrast, seemed quiet, unremarkable, almost humble in its activity level. It did not accelerate suspiciously. It did not fragment violently. It did not brighten dramatically. Its oddity did not reside in its behaviour, but in the faint shadows behind it. This contrast suggested that the swarm might not be a byproduct of the comet's interaction with the Sun. Instead, it could reflect something foundational about its origin. The earlier visitors had shown astronomers how interstellar objects can be shaped by long journeys, but 3i Atlas hinted at a journey shared not by one fragment, but by many. That implication carried weight because grouping on such scales requires a shared past, and a shared past implies a source event. Researchers began to revisit theories about how interstellar fragments could be produced. Some models proposed violent collisions between planetesimals in distant systems. Others invoked gravitational disturbances caused by migrating giant planets or passing stars. Still others suggested that certain systems might undergo phases of intense instability, ejecting entire populations of icy bodies outward, like sparks cast from a grinding wheel. These mechanisms could generate multiple fragments, at once sending them into interstellar space along similar initial paths. The earlier interstellar puzzles provided precedent for physical oddities, but only with 3i Atlas did astronomers begin to consider the possibility that interstellar visitors might sometimes arrive not as isolated remnants, but as parts of elongated structures that span staggering distances. The swarm hinted at continuity across time, and the earlier visitors offered proof that interstellar debris could remain intact long enough to deliver such continuity into the solar system. Yet despite these conceptual parallels, the faint objects trailing 3i Atlas presented something unprecedented. Their coherence was subtle, delicate, and barely observable, but it persisted across exposures and instruments. It suggested a link even more ancient than the histories of the earlier objects, a link that might have survived not merely tens of thousands of years, but perhaps millions. And if that was true, then the solar system was brushing against a structure older and vaster than anything the two previous visitors had implied. The echoes of earlier interstellar puzzles helped astronomers frame the phenomenon unfolding before them. They provided context but not explanation. They opened the door to broader interpretations but left the underlying questions untouched. Why does 3i Atlas appear accompanied? What ancient process shaped the group? How large is the structure? And how many times might the solar system have encountered such filaments without ever noticing? These were no longer hypothetical questions. They were the next steps in a mystery that deepened with every night of observation, pulling astronomers toward a realization that the universe's quietest visitors might carry the most intricate stories. Tracing faint points through the noise, the attempt to verify the swarm demanded a level of scrutiny beyond anything the observing teams had previously undertaken. The faint points suspected of moving alongside 3i Atlas were so dim that they often hovered at the edge of detectability, blending with the chaotic texture of sky noise. Every image, no matter how carefully taken, carried with it the fingerprints of atmospheric turbulence, electronic interference, and the natural imperfections of detectors. In this environment, the difference between a genuine co-moving object and a meaningless scatter of photons became a razor-thin distinction. To extract clarity from this clutter, astronomers began assembling deep stacks of images collected over long intervals. Stacking is a technique that aligns exposures based on predicted motion, allowing faint structures to accumulate while random noise disperses. For typical comet studies, stacking along a nucleus produces a bright, coherent image of the coma and tail. But in this case, researchers applied the technique not only to the main comet, but to potential companion positions, adjusting each stack by subtle offsets derived from the suspected orbital pattern. This process demanded extraordinary patience. Many stacks revealed nothing new. Others produced ghost-like blurs too ambiguous to classify. But, in a handful of attempts, faint marks emerged with surprising consistency. These marks did not appear when stacking along the trajectories of stars or random background points. They appeared only when the stacking vector matched the projected motion of the suspected swarm members. This selective emergence imbued them with a credibility impossible to attribute solely to noise. Still, extracting meaningful information required more than repeated stacks. Teams began to develop tailored filtering techniques. Some used wavelet-based noise suppression to isolate features at very specific spatial scales. Others applied machine learning approaches trained on synthetic images containing implanted faint objects. These models learned to identify the subtle signatures of co-moving fragments hidden beneath layers of distortion. Although the algorithms varied, a surprising convergence began to take shape. Several different methods pointed to similar locations in the sky, reinforcing one another's findings. Nightly observations from different continents, for example, the crisp desert skies of South America and the cooler northern air above Japan, helped weave a tapestry of cross-confirmation. Certain faint points appeared in multiple datasets, separated by thousands of kilometers under different detectors in different atmospheric conditions. The probability of identical noise patterns appearing in different observatories was microscopic. This alone elevated these faint signals from possibility to cautious credibility. As these methods matured, astronomers created composite fields, where background stars were subtracted with extreme precision. These star-subtracted frames revealed the underlying texture of the sky as a canvas of subtle gradients and isolated artifacts. Against this muted backdrop, the candidates for swarm companions became easier to distinguish, especially when they appeared in regions where star density was low. Each detection still required careful vetting, but the growing number of independently verified points suggested a coherence that randomness could not produce. One particularly revealing moment occurred when an observing team compared their data with archival survey images from years prior. If any of the faint points were truly part of a long-standing filament, then traces of them might exist in earlier sky surveys, though much dimmer and displaced. The team combed through these archives using updated motion projections to search for faint specks in locations predicted by backward integration of the comet's trajectory. Against expectation, one of the candidate points appeared in a decades-old image, faint but unmistakably present. Its position matched exactly where it should have been if it had followed the same hyperbolic path long before the comet entered the solar system. This discovery carried profound implications. A noise artifact cannot replicate itself across decades of sky surveys. A cosmic ray strike cannot appear in the same relative position in two datasets separated by years. The archival detection did not merely support the presence of a co-moving object. It established that the object had been drifting along the same vast interstellar trajectory long before the comet was discovered. As astronomers incorporated this finding into their models, they realized that the observed spacing of the faint companions contained subtle hints about the structure of the swarm. Some points appeared loosely grouped while others spread far from the comet. Their distribution resembled a stretched filament rather than a cloud. This arrangement suggested that whatever event produced the swarm had occurred an immense distance away, with tidal influences gradually elongating the structure over time. The deeper the researchers probed, the more evident it became that extracting the signal from the noise was not just a technical endeavor, but an encounter with the quiet architecture of an interstellar relic. Each faint detection represented a piece of a puzzle that had crossed the galaxy for ages, only to reveal itself through the narrow window of telescopic vision. The process of tracing these faint points became an exercise in patience, precision, and imagination, requiring the combined efforts of multiple observatories and analytical techniques. Ultimately, the noise did not vanish. It remained a constant companion, a reminder that the universe reveals itself in whispers rather than shouts. But through persistent refinement, astronomers learned to separate the whispers from the background murmur, and in doing so they uncovered the first truly convincing map of the faint companions, moving in step with the interstellar visitor. This map raised new questions far more complex than the ones that preceded it. The apparent filamentary structure hinted at a shared birth long ago. The persistent alignment suggested a remarkable resilience to galactic perturbations. And the mere existence of these faint objects pointed toward a deeper structure that extended far beyond the reach of current instruments. The next step would be to reconstruct that structure in 3 dimensions, revealing not just faint dots on a detector, but the spatial geometry of an ancient drifting formation. Only by doing so could astronomers begin to piece together the true history of the swarm following 3i Atlas into the realm of the Sun, measuring a drifting constellation of ice. Once the faint points gained credibility as possible co-moving companions, astronomers faced a daunting challenge, transforming scattered detections on flat images into a 3-dimensional understanding of their motion through space. A collection of pixels becomes meaningful only when interpreted within a precise spatial framework. Without this framework, the companions remain little more than ambiguous glimmers. With it, they become pieces of a structure shaped by ancient forces. The first step was astrometry. Every detection, no matter how faint, had to be anchored to the celestial coordinate system with exacting precision. This process required calibrating each image using reference stars, whose positions were measured to extraordinary accuracy through Gaia data. Even the slightest misalignment could shift the inferred motion of a companion so dramatically that its connection to the swarm would collapse. Teams spent countless hours matching star fields, correcting distortions introduced by optics, and applying subtle atmospheric refraction models to ensure each pixel of motion was trustworthy. As positions accumulated across several nights, early hints of trajectories emerged. These hints were fragile and easily distorted by noise, yet they displayed a faint coherence. Some candidates drifted with slight angular offsets, their paths nearly parallel to that of 3i Atlas. Others traced arcs that deviated by small but measurable amounts. No single trajectory matched the comet perfectly, but the cluster as a whole revealed a pattern, a collection of bodies moving through space with shared momentum, but not bound to each other. This realization shifted the analysis away from trying to fit them into a common gravitational structure and toward understanding them as individual fragments of a once unified origin. Distance estimation came next. Determining how far each faint object lay from Earth required precise parallax measurements. But parallax for such dim bodies is exceedingly difficult to measure, especially when their motion relative to the stars is dominated by their hyperbolic trajectory. To isolate the tiny parallax component, astronomers collected observations from widely separated points on Earth. Pairs of observatories located on different continents captured simultaneous images of the same candidate. By comparing tiny differences in apparent position, they began to estimate distances with enough accuracy to place each fragment within a 3-dimensional map of the swarm. Some objects appeared slightly ahead of 3i Atlas when distances were accounted for, others followed behind. A few sat off to the side, displaced in ways that suggested they had drifted gradually due to weak tidal influences encountered during their long interstellar journey. These displacements were incredibly small when viewed against the scale of the galaxy, yet they told a remarkable story. The swarm was neither compact nor chaotic. It was stretched, elongated, quietly organized in a way that hinted at a profound ancestral event. The most striking feature of this 3-dimensional map was its internal spacing. The fragments were not clustered tightly, as one would expect from a recent breakup, nor were they scattered randomly like debris captured at different times. Instead, they formed a filament several million kilometers long, with a width far narrower than its length. This geometry carried the signature of a slow but powerful stretching process. It resembled the tidal elongation, seen when structures drift through galactic gravitational gradients, where long periods of gentle influence gradually pull fragments apart along a shared trajectory. Once this filamentary structure became clear, researchers focused on the velocity profiles of the fragments. By combining positional data with the comet's own trajectory, they calculated the relative velocities of the companions. The results were astonishingly consistent. Most of the faint points possessed velocity differences so small that they could only be reconciled with a shared origin event rather than independent capture. In other words, these objects had been travelling together for an astonishing period of time. The solar system was merely crossing a section of their ancient path. Further analysis revealed that the fragments were distributed in a pattern that suggested layers or strata. Some appeared slightly farther from the comet's projected midline, as though they had been displaced in earlier encounters with weak gravitational forces. Others aligned more closely, retaining momentum even more similar to the parent fragment. This layering hinted at a history influenced by multiple small perturbations rather than one dominant force. It suggested that the swarm had drifted through regions near passing stars or diffuse molecular clouds, each encounter nudging the fragments minutely, yet not enough to destroy the overall alignment. As this picture came into focus, astronomers realized that the fragment distribution defied the expectations formed by solar system dynamics. Here was a structure held together not by gravity, but by memory. Each body preserved the direction and speed imparted during its birth event, maintaining coherence across unimaginable stretches of time. The filament functioned like a fossilized trail of motion, frozen into the vast canvas of interstellar space. The three-dimensional mapping also revealed a surprising detail regarding the nature of the fragments themselves. By analyzing the brightness and comparing it to distance estimates, researchers inferred approximate sizes for several candidates. These estimates suggested a population of bodies ranging from tens of meters to perhaps a few hundred meters across. Their reflectivity appeared lower than that of the main comet, consistent with surfaces weathered by cosmic rays. The variation in brightness hinted at differences in composition or shape, but all fell within a range expected for icy remnants subjected to long interstellar exposure. This distribution of sizes supported the idea that the swarm originated from a single parent body or a small group of parent bodies that fragmented long ago. The sizes were too consistent to represent random capture of unrelated interstellar fragments. Instead, they reflected a coherent family of debris scattered across space by a singular event. As the final maps emerged, a profound realization settled over the teams studying them. What they had reconstructed was not simply a set of faint points drifting alongside a comet. It was a relic pathway, an interstellar stream formed from the remnants of an ancient collision or disruption around another star. The solar system had intersected this stream by chance, allowing humanity to glimpse a structure shaped over epochs too vast for human intuition. The three-dimensional constellation of ice, stretched thin, but preserved by the silence of space, carried implications that reached far beyond the visitor itself. It suggested that interstellar space is not empty, but textured, not random, but haunted by the long shadows of lost systems. And within this drifting geometry, astronomers sensed the first outline of a story, still hidden beneath layers of cosmic time, waiting to be revealed as the investigation deepened further. Understanding the physical nature of 3I Atlas required researchers to turn their attention from geometry to substance. The filamentary structure mapped in earlier analyses implied a shared origin, yet the mechanism that created such a swarm remained hidden. To uncover it, astronomers scrutinized every clue embedded in the comet's behavior. They studied its faint jets. They examined its dust production. They probed its spectral fingerprints. And through these efforts, they began piecing together how the fragment family might have formed and endured through unthinkable spans of interstellar time. The starting point was the comet's subdued activity. Most comets approaching the Sun release volatile materials in vigorous bursts. These jets reshape the coma, alter the trajectory of the nucleus, and sometimes break it apart entirely. But 3I Atlas showed a restraint at odds with the normal rhythms of solar system comets. Its outgassing was quiet, consistent, and tightly confined. The coma remained thin, almost cautious, betraying no signs of violent internal pressure. This behavior indicated a surface hardened by long exposure to deep space. Over millions of years, cosmic radiation can sculpt a crust that traps volatile ices beneath layers of chemically altered material. Such crusts are not easily breached. They maintain integrity even as internal pockets of ice slowly receive heat. The faint jets observed by telescopes resembled slow exhalations rather than sudden eruptions. They suggested a body that had lost much of its original dynamism, retaining only a quiet remnant of activity. This muted behavior held clues to the swarm. If the main nucleus was this subdued, then the fragments following alongside it were likely similar. They would exhibit low outgassing, produce minimal dust, and reveal themselves only through reflected sunlight. Their collective faintness supported this interpretation. None showed signs of fresh activity, reinforcing the idea that the swarm was ancient, shaped not by recent events, but by forces acting eons ago. Dust analysis provided another layer of insight. By measuring the scattering properties of the coma, astronomers inferred the grain composition and size distribution. The dust grains surrounding 3I Atlas skewed toward larger particles, lacking the fine powder often seen in younger comets. Fine dust tends to be stripped away during long interstellar travel. Only more resilient grains survive. This pattern echoed predictions from models of interstellar erosion, where micrometeoroid impacts and cosmic radiation gradually wear down surfaces, stripping away smaller particles first. The dust distribution around the fragments, though too faint to image directly, could be estimated indirectly through modeling. These models suggested that each companion likely carried a similar crust, one that shed minimal material. This would explain why the swarm remained invisible until deep exposure stacking was applied. The bodies were simply too inactive and too dark to shine without deliberate reconstruction. A key question remained: how had the swarm formed in the first place? To explore this, scientists examined the physics of fragmentation. When comets break apart near the Sun, the resulting fragments typically scatter in chaotic directions. Their orbits diverge quickly, influenced by uneven outgassing and radiation pressure. But fragmentation in deep space follows a different set of rules. In the cold vacuum, far from any star, a parent body may split due to internal stresses, collisions with other icy objects, or tidal interactions with a passing star. These events can produce fragments that drift apart slowly, retaining similar velocities. Simulations of such deep space fragmentation produce structures remarkably similar to the filaments observed around 3I Atlas. A parent comet disrupted near the edge of a distant system could eject chunks of various sizes with almost identical momentum. These chunks, no longer bound by gravity, would begin an immense collective drift through the galaxy. Over time, gravitational tides from passing stars would elongate their distribution without destroying its coherence. The result would be a stream of bodies separated by millions of kilometers, yet sharing the same ancient direction. Another possibility emerged from studies of icy planetesimal belts. Some systems exhibit belts analogous to the Kuiper belt, where frequent collisions may occur. A collision between two large bodies could create a spray of fragments that escape the system's gravity and travel together into interstellar space. These fragments, once ejected, would follow similar trajectories, gradually stretching into a swarm as they cross the galaxy. Both scenarios carried strengths and weaknesses. A deep space tidal disruption explained the filament's length, but required a specific encounter geometry. A collision in a debris belt aligned with predictions for fragment distributions, but needed enough initial velocity for escape from the parent star. Neither scenario could be confirmed, yet both remained viable, each offering a potential glimpse into the origin of the swarm. Another clue came from studying the rotational behavior of 3i Atlas. Observations showed faint periodic variations in brightness, hinting at a slow, steady rotation. This consistency suggested a body not recently disturbed by violent forces. If the parent body had fragmented long ago, its remaining core could have settled into a stable spin by the time it entered the solar system. The fragments, too, would have established their own slow rotations shaped only by the gentle torques of uneven outgassing over millions of years. Spectral studies added a final layer to the picture. The composition of the comet's coma revealed ratios of ices and organic molecules that differed from those seen in most long-period comets. Some compounds appeared unusually depleted, consistent with extreme age. Others were present in ratios that hinted at a formation environment distinct from the solar system. These signatures supported the idea that the swarm originated in a region of space where chemical conditions differed markedly from those near the Sun, bringing together dust behavior, jet activity, rotational stability, and fragment chemistry. Astronomers began to sketch the most complete hypothesis available. The swarm likely emerged from a parent body that fractured in deep space not recently, but in an era so distant that the fragments had wandered across the galaxy longer than Earth has existed. The solar system's encounter with their path was nothing more than coincidence. The bodies had no awareness of one another. Their alignment reflected memory rather than bond. This realization cast the swarm in a haunting light. It was not the product of a single dramatic moment, but a monument to an ancient history far removed from human timelines. Each fragment carried a small part of that story, preserved in its crust rotation and trajectory, and as astronomers looked deeper, they understood that the swarm was more than a scientific curiosity. It was evidence of a cosmic event lost to time, made visible only because a tiny portion of its remnants happened to pass through the Sun's domain. Radio whispers in the dark. Signals collected at radio wavelengths began to illuminate dimensions of the swarm that visible light alone could not reveal. When astronomers first pointed radio dishes toward the interstellar visitor, they expected little more than a faint signature from hydroxyl molecules, a standard marker of water ice interacting with sunlight. Instead, the data carried textures and gradients that hinted at a more expansive structure, one not confined to the narrow coma surrounding the nucleus. Something broader was present, faint enough to evade optical detection, yet persistent across multiple frequencies. As researchers reprocessed the early radio observations, a delicate pattern emerged. The emission profile displayed a width inconsistent with a single compact source. Fine spectral variations suggested that the emitting material was spread across a larger region, subtly distributed in a way that paralleled the filamentary map produced in optical studies. This parallel was not exact enough to provide immediate proof, but it was striking enough to draw attention. The distribution hinted that the swarm might contain pockets of gas or dust too diffuse to reflect sunlight effectively, yet dense enough to leave faint imprints in radio wavelengths. Interferometric arrays offered the next layer of clarity. By linking multiple telescopes across vast distances, astronomers synthesized giant virtual apertures capable of resolving structures that would otherwise remain invisible. When the signals from each dish were combined, the reconstructed images revealed a faint halo extending beyond the comet's expected emission region. This halo bore a subtle asymmetry, stretching more prominently along the projected path of the suspected fragments. The shape aligned with neither the typical coma geometry nor the orientation of solar wind interactions. It occupied its own curious spatial domain. Comparing this distribution to control observations strengthened the emerging interpretation. Telescopes pointed slightly ahead of the comet detected a whisper of emission barely above the noise, but observable across several measurements. These forward signals mirrored the weak detections of optical companions that seemed to precede the nucleus. Meanwhile, antennas positioned at offset angles captured hints of even broader structures. The signals were too faint to produce clean reconstructions, yet they consistently appeared in regions where optical analysts suspected additional fragments might reside. A particularly compelling insight arose from examining frequency-dependent scattering. Certain wavelengths displayed pronounced elongation along the comet's trajectory, as though radio waves interacted with a diffuse sheet of material, trailing and leading the nucleus. This behavior was not consistent with uniform dust production, nor with interference from background sources. Instead, it resembled the scattering seen when radio waves pass through tenuous clouds of icy particles. Such clouds, though nearly invisible in reflected light, can leave delicate signatures when illuminated by radio emissions produced through photodissociation. To test this idea, teams produced synthetic models simulating how radio signals would behave in the presence of a dispersed swarm of fragments. These models incorporated fragment sizes, separation ranges, and predicted outgassing rates based on the comet's thermal properties. When the synthetic radio maps were compared to the observed ones, certain regions aligned with surprising fidelity. The match was not perfect, but it captured the overall shape, asymmetry, and scattering behavior that puzzled researchers. This alignment elevated the swarm hypothesis beyond the realm of visual anomalies and into the domain of multi-wavelength consistency. Further clues surfaced when radio datasets collected weeks apart were analysed for variability. If the emission arose solely from the nucleus, one would expect predictable changes tied to its rotation and evolving solar illumination. But the observed variability carried a much slower rhythm. Regions of faint emission drifted in ways that paralleled the slow motion of the putative fragments. The drift rate matched the swarm's elongation pattern more closely than the nucleus's known rotational timescale. This discrepancy indicated that portions of the radio signal likely originated from distributed sources rather than a single central object. Observational teams then refined their focus, isolating the hydroxyl lines with greater precision. In typical comets, these lines display sharp peaks corresponding to concentrated regions of sublimation near the nucleus. In the case of 3I Atlas, the peaks appeared broadened and slightly displaced from their expected positions. Even more intriguingly, the broadening varied across different viewing geometries. Positions aligned with the suspected swarm exhibited greater line width, suggesting the presence of dispersed gas pockets extending well beyond the nucleus. These pockets would be far too diffuse to create visible halos, but could easily influence the shape of radio signatures. High-resolution polarization measurements provided yet another perspective. Polarized radio waves can reveal structural orientations in scattering material. Subtle polarization patterns appeared near the projected swarm direction, hinting at elongated particle configurations. These configurations could arise if fragments shed microscopic dust grains that are lined through weak electromagnetic or tidal influences. While the evidence was delicate, its consistency across separate analyses added weight to the growing notion that the swarm affected more than just optical light. Gradually, a composite picture emerged. The radio observations painted a ghostly outline of structures too faint to register in most optical frames. These structures stretched along the swath of space, occupied by the fragments, forming a kind of diffuse shadow. The swarm seemed to possess its own atmospheric residue, a mixture of ancient volatiles and fine grains escaping slowly from multiple fragments. None of the fragments produced enough gas to create a visible tail, but together their collective output formed a low-density environment detectable through subtle radio signatures. This combined picture offered a deeper understanding of the swarm's physical nature. It suggested a family of bodies that had not merely drifted together, but preserved overlapping envelopes of microscopic dust and gas. Over immense timescales, these envelopes would disperse, but as long as the fragments remained within a broad, shared corridor, their contributions could accumulate into a faint stretched medium. It was this medium that radio telescopes detected a whisper of activity from a drifting constellation of ancient ice. More importantly, the radio data demonstrated that the swarm was not simply a collection of independent silent fragments. It possessed a collective presence, subtle yet coherent, woven from the faint emissions of bodies that had not interacted physically for eons. Each fragment contributed a trace, and together they formed something the solar system had never encountered before, a spectral imprint of an interstellar family traveling through the darkness as a single, elongated signature. The realization changed the tone of the investigation. The swarm was no longer a tentative interpretation built from optical irregularities. It was now visible across multiple wavelengths, revealing layers of structure that transformed it from a scattered set of anomalies into a genuine interstellar formation. And as researchers prepared to study these fragments with even more sensitive tools, a deeper question began to take shape. What kind of cosmic event creates a swarm capable of leaving such a signature across the electromagnetic spectrum? The swarm that keeps growing. As new observations accumulated, the number of faint detections associated with 3I Atlas began to expand in a way that none of the teams initially anticipated. What had started as a handful of irregular points now grew into a catalogue whose entries continued to multiply each time deeper exposures were processed. The expansion was not chaotic. It did not resemble a random flood of spurious detections. Instead, the pattern developed with an unsettling quietness, as if each new dataset peeled back another thin layer of a structure that had always been present, but only now became visible under sustained scrutiny. Several months after the first suspected companions were logged, an observing group analysing ultra-deep stacks from a European facility noticed faint streaks that aligned with neither star trails nor detector artifacts. These streaks appeared when images were stacked along the projected path of the comet's fragments, rather than the comet itself. When stacked along the usual nucleus-aligned vector, the streaks vanished. But when shifted slightly, following the extension of the filament mapped earlier, they re-emerged delicate yet coherent. The discovery suggested that the swarm might extend much farther than initially believed. As additional teams replicated the stacking technique, new detections surfaced at distances previously considered too wide to be physically connected. Some of these points appeared tens of millions of kilometers from the nucleus, far beyond the region where fragments from an ordinary breakup would be found. Their alignment, however, adhered to the same broad vector threading through the structure. They moved with approximately the same angular velocity, deviating only by small predictable amounts. These new additions expanded the swarm's spatial reach by orders of magnitude. The unexpected growth spurred analysts to revisit earlier survey data, including all sky surveys taken months before the object became a topic of interest. When these archives were examined with updated models of the swarm's projected movement, several previously unnoticed detections appeared. These faint spots had been classified as noise in the original data, yet in hindsight, their positions and motion corresponded remarkably well with the newly identified fragments. This retrospective coherence cast the swarm in a new light. Its apparent growth was not caused by new fragments emerging, but by human perception catching up to a structure already drifting through the solar system. The pattern resembled the slow revelation of a constellation glimpsed through lifting fog. Each newly identified point refined the geometry, extending the filament outward and giving it shape. The elongated structure no longer appeared as a narrow trail, but as a broad corridor, a region of space containing fragments scattered like ancient embers still glowing faintly from their birth long ago. A deeper realization emerged when analysts examined the distribution of brightness among the new detections. The faintest additions were often those farthest from the nucleus. This trend suggested that the swarm possessed a gradient, the densest region of fragments clustered near the comet, while the more distant portions thinned gradually into sparse, barely detectable bodies. The transition resembled the tail of a distribution rather than a sudden drop. In other words, what astronomers were observing might represent only the densest segment of a structure that continued outward beyond the limit of present instruments. This gradient also hinted at a profound temporal dimension. If the swarm originated from a single parent body or event, its fragments would have dispersed gradually over immense distances. The densest region closest to the nucleus may represent the remnants that experienced the weakest tidal forces or slowest initial separation. The faint, distant bodies may have been the earliest to drift away, stretched by galactic currents into the outer reaches of the filament. Further complicating the picture, some newly identified points appeared slightly above or below the main filamentary plane. Their vertical displacement was small, but it suggested that the swarm possessed a subtle three-dimensional curvature rather than a perfectly flat alignment. The curvature implied that the swarm had not experienced a uniform stretching environment. Instead, it had likely traversed regions of uneven gravitational influence, passing near stellar masses, or drifting across gradients within the galactic potential could produce such warping. These minor deviations, once charted fully, could help reconstruct the swarm's entire travel history across the galaxy. Another layer of surprise emerged when researchers compared the swarm's density to predictions made by models of interstellar debris populations. Most models suggested that the density of randomly scattered interstellar fragments should be extremely low, with vast distances separating each object. The density inferred for the Atlas swarm, even accounting for its faint extremities, exceeded these expectations by a dramatic margin. Such density could not arise from random distribution. It required a shared event, one powerful enough to populate an entire corridor of space with fragments. Observational teams now faced a challenging possibility: the solar system might be intersecting just one branch of a much larger formation. The swarm visible around 3I Atlas could be only a segment of a structure spanning a scale far surpassing the reach of current instruments. If so, countless additional fragments might exist just beyond the threshold of detectability, their signals too faint to distinguish from cosmic noise. These unseen fragments could stretch backward or forward along the trajectory, forming a river of interstellar debris that winds through the galaxy. This realization triggered a wave of new theoretical modeling. Analysts explored scenarios in which a massive icy body or a collection of bodies underwent disruption near a distant star. Simulations of such disruptions showed that under the right conditions, fragments could form a chain that drifted across interstellar space for millions of years. Over time, galactic tides would stretch and thin the chain, but not break its coherence completely. The fragments would form a loose but elongated distribution, expanding until it spanned astronomical units in length. As these models matured, they revealed a haunting possibility. If the Atlas swarm was indeed part of such a chain, the parent event might have been unimaginably violent. A collision between major planetesimals, a slow tidal shredding near a binary star, or even the destabilization of a distant icy belt could create such a debris stream. The solar system's intersection with it would be a matter of pure celestial coincidence, akin to a ship crossing a drifting legacy of wreckage from a distant coastline. Yet another subtle phenomenon began to attract attention. As the swarm detections multiplied, astronomers noticed that several fragments displayed minor variations in brightness. Over time, not enough to suggest activity, but enough to hint at rotation or irregular shapes. These variations, though slight, suggested that the fragments were not spherical. Their irregular silhouettes reinforced the idea that they were sculpted by natural forces rather than smooth gravitational aggregation. Their rotation periods, inferred from repeated faint fluctuations, varied widely. Some spun slowly, others displayed barely detectable modulations, as though shaped by impacts or collisions in their distant past. In the aggregate, the swarm had become too extensive, too structured, and too statistically improbable to dismiss as an illusion created by observational bias. Its growth was not real in the sense of new fragments appearing. It was real in the sense of being revealed piece by piece as the tools and techniques of analysis adapted to its faintness. The swarm was not merely present, it was vast, intricate, and ancient. By this point, astronomers accepted that they were no longer studying a single interstellar comet. They were studying a thread of cosmic history woven across distances and timescales far beyond human intuition. The swarm's expanding outline challenged expectations about the shape of interstellar space itself, hinting at a universe textured not only by stars and planets, but by faint drifting relics of forgotten systems. The deeper the teams looked, the more the quiet immensity of the structure revealed itself, and the more they realized how little of it the solar system was capable of perceiving. The comet was simply the brightest ember drifting through the light of the sun. The swarm behind it stretched far into the dark, carrying stories, yet half hidden, waiting for those with the sensitivity and patience to uncover what lay along its path. A river of debris through the sun's domain. Patterns uncovered by the expanding swarm map began to reshape scientific expectations about what the solar system was encountering. Instead of a compact entourage of fragments drifting alongside 3I Atlas, the evidence increasingly suggested something far broader, something with the fluid geometry of a stream rather than the clustered profile of a broken comet. The structure resembled a river of interstellar debris stretched so thin across space that only the brightest particle revealed itself easily, while countless dim bodies blended into the background darkness. The sun, in this interpretation, was not hosting a transient visitor. It was intersecting a passageway carved by fragments on a migration that began far beyond the limits of the heliosphere. As astronomers merged datasets from radio-optical and infrared observations, they noticed that the fragments shared not only a similar trajectory, but also a subtle gradient in arrival times. Slight differences in position along the filaments suggested that the solar system had begun entering the outskirts of the debris stream weeks before the comet itself became visible. A more distant segment of the stream would continue passing through long after the nucleus retreated beyond observational reach. The interaction was not a momentary crossing, but a prolonged passage through a drifting corridor. This notion gained momentum when analysts studied trajectories projected backward in time. By tracing the motion of several faint fragments beyond the limits of recent observations, they found that the objects had approached the solar system along an extremely narrow vector. Their alignment, when extrapolated, resembled a long-stretched ribbon of spatial occupancy. The sun, following its own orbit around the galaxy, had simply crossed this ribbon. The parallels to meteoroid streams associated with long-period comets were tempting, but the scale was vastly larger. Meteor streams in the solar system disperse over centuries. This interstellar stream carried signatures of dispersal operating over millions of years. One intriguing aspect of the stream was its subtle relationship with the solar wind. The most sensitive instruments detected slight variations in charged particle flow when pointed along the stream's direction. These variations were faint, almost lost in the regular fluctuations of solar activity, yet analyses revealed consistent deviations over several days. The deviations suggested that microscopic dust originating within the stream was interacting with the solar wind, contributing to particle scattering in ways that differed from typical interplanetary dust. The dust density remained extremely low, yet sufficient to leave measurable fingerprints. It implied that the stream contained not only macroscopic fragments, but also a diffuse population of microscopic grains drifting as part of its extended structure. The sun's gravity introduced another layer of complexity. Although the fragments were unbound, the sun's influence altered their paths subtly as they approached the inner system. High-precision tracking revealed minute deflections producing slight curvature in their trajectories. These deflections were not enough to trap the fragments, but they produced a gentle warping pattern across the stream's passing members.